Hi, everybody. Sorry for the Zoom debacle. For whatever reason, Zoom thought it would be a good idea to just delete our recurring meeting for the class. It just did that automatically. I'm not sure if that's like a New Year's thing, but it's really weird. It actually deleted all of our recurring meetings except for one that was made in the last couple of days. But hopefully everybody's going to make it in, and if they aren't, it doesn't look like anyone's having any trouble at this point, so that's good. Today we're going to talk about the geometric distribution, and we've got we've got a slide deck for it. I'm just similar to the last couple discrete distributions, I'm not going to work off of that slide deck. I am going to kind of talk us through, and we'll peek at a couple slides, but most of this will be similar to the last couple of discrete distributions lectures. So yeah, that said, let's talk about the geometric distribution. I'm going to go ahead and share my screen. Actually, give me 1 second. Okay, good. All right. Yeah, when we're thinking about the geometric distribution, we're thinking about a series of Bernoulli trials, similar to binomial, but there's a difference here. In this case, we're considering the number of failures up until some success. And so K here represents the number of failures up to and including the first success, or up to but not including the first success. And you'll notice we have two different versions of the PMF here, but that doesn't really matter. It doesn't really matter which one you use. So we're going to code both of them, and we're going to code both of them into a given function. And let me pull up this. So yeah, let's think about this. Easy way of thinking about the geometric distribution, you're flipping a coin, and it's a fair coin. What is the probability that you're going to get heads on the 5th trial, for instance? So what does that mean? It means that you're going to get tails, 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 and then heads. And here, right, this is our first success, right? This is where we're like, wow, there's our first success. So we never really consider more than one success in a geometric distribution. We only consider the first success. And how we define this, how we describe the first success in terms of the PMF, in terms of getting the probability of getting success on the 5th trial, we either say K is success on the 5th trial, right? So there's two ways to think about this. Success on the 5th trial, or K is the probability of 4 failures before success. Right? So we've got these two definitions of K that we can use. So we're going to choose one of these in general, and most people will prefer one over the other. But like I said, just to kind of think about this in terms of coding, we're going to code functions that use either what I'm going to call the inclusive form, right, where we're talking about the trials up to and including the first success, or what I'll call the exclusive form, which is the number of trials before the first success, right? So those are the two versions of this. Notice that these look very similar, right? It's 1 minus the probability raised to K minus 1, or it's 1 minus the probability raised to K. And, you don't need to know which one of these to use. It's not that. You're going to use one of them and just know the definition of it, right? So if you know that you're using the inclusive PMF, then, and we're talking about this problem that I'm describing here, if you know you're using the inclusive PMF, then k equals 5, right? If it's inclusive, k equals 5. If it's exclusive, k equals 4. You know, really I should say k equals 4, right? As in 4 failures. So it's either success on the 5th trial or 4 failures. Those mean the same thing. You're going to get the same result, right? It's going to be the same probability. You just need to know which PMF you're using. So with that said, I realize I do not have a terminal open, and I should really do that. And that's just going to take me a quick sec. So let's go trauma, normalize, premium prep, and November 30th. And then I think we're to git watch. And we're in stats, and we're 0.5, discrete distributions, and geometric. And so we've got 3 files that we're working with here. We've got geometric using PMF, geometric sampling, and geometric problems. But in reality, we're probably just going to play around with geometric using PMF and geometric sampling, and we might jump to a more generic kind of discrete problem away from geometric. But there is something cool about the geometric distribution that I want to show you, and I'll do that at some point today. So let me make this big enough to see, and hopefully this will open a code editor right here, and it did, instead of opening it in some random place, which it sometimes does. And I'll just open these files so we have them. We have them ready. Okay. So so yeah, let me just reiterate a couple things about the geometric distribution. So you know, geometric, as I said, it models the number of failures up until the first success. And we consider we can consider k. K means one of 2 things, right? It's the number of Bernoulli trial failures before the first success, or right, the number of Bernoulli trials up to and including the first success. We've got both of those formulas here, both these PMFs here. They're honestly, like, if you look at them, they're very simple, right? And if you played around with log odds or you know, other, well, we even see something that looks like this in the binomial PMF, right? So this construct, this mathematical construct, should start looking more familiar as you see more formulations. And you know, we won't talk about that deeply here, but this is going to be something that a mathematical idea that comes back around and around and around. So I'm going to have you, well, we'll start this off with some coding. And I'm going to have you write the geometric PMF. Okay, so write the geometric PMF function. There are going to be 3 parameters that you put into this function, that you define for this function. One is going to be the probability, P, right? So if it's a 50-50 chance, notice that 1 minus 0.5 raised to the number of failures multiplied by 0.5, right? Fairly straightforward, easy math. K is going to be the number of failures. And then this is going to be inclusive or exclusive of the first success. And if you're thinking about it, well, then we need some other parameter that tells us if we're using inclusive or exclusive. And let's say that we have inclusive, And let's default that to true. Like we'll just assume we're going to use the inclusive, although we'll write these functions to use either. So this is just right whether or not to use inclusive or exclusive PMF. So I'll give you the function header just to make sure you make sure you're clear on what we're asking for here. So geometric PMF, and it's going to be probability k and inclusive gets true. All right. So let's do 3 minutes. Well, let's do 4 minutes on this, and yeah, do your best, and then we'll code it out, and we'll continue on with geometric. Oh, am I not screen sharing? No, I am. Oh, strange. It's just not showing me any of them. Okay, never mind. We're good. All right, so I'm just going to code through this really quick. It should be pretty straightforward, I think, because we're just translating these directly, and we just have this flag, this setting, this switch that's, if inclusive, well, then we use the inclusive form, which is just p times, I usually write p first, and then I do p times 1 minus p, and 1 minus p to the k minus 1. And otherwise, notice I don't need this else here, of course, but and usually I wouldn't personally write it, but I'll go ahead and write it here. Here we are doing 1 minus p to the k. So let's contextualize this, and let's use it with a story problem. And about you are handing out coupons for a restaurant. The probability that someone accepts a coupon is about 0.47. How about that? And let's ask the question, what is the probability? Make that a little bigger. What is the probability that the first person who accepts a flyer is the third person you offer a flyer? So let's just take a minute on this and show the form of this for inclusive equals true and for inclusive equals false. And I'm just going to set a 1 minute timer for you to answer this. So, I like to do this thing where I write down what I know. And so I'm going to just do that first. We're going to call out to this twice, one time with inclusive equals true, the other time inclusive equals false. And we're talking about the probability that someone accepts a coupon. And so we know the probability, right, as 0.47. And then we want to determine the value of k, right? So k is the, we're considering was the probability that the first person who accepts a flyer is the third person you offer a flyer. Well, let's relate these two to each other, and I'm just going to say k is 3. Well, k is 3 if we are inclusive of the third person as a success, right? So here we're saying k, and here we would say k minus 1, right? And I should probably put print statements around these. And let's go ahead and run that. Oh, I am in the wrong file. That's cool. Okay, you know what? Let me just fix that really quick. funny. Okay. So we shouldn't be in geometric problems. We should be in geometric using PMF. Sorry about that. So let's do that again using PMF. And we get 0.132, right? And that looks pretty consistent. Now, the thing is, I noticed a number of you, when you set it to true and then set it to false, you didn't change K, right? We have to think of K as being different when we use an inclusive PMF over the exclusive PMF. The reason, and I'll just jump back over to this drawing, we're talking about success on the third person, right? So we've got person 1, failure, person 2, failure, and then person 3, success. They take the coupon. Either we think of K as being the position of the success, right, which is 3 in this case. So here, if we're being inclusive of the success, then K is 3. If we're being exclusive, then K is 2, or K is 3 minus 1, right? And so the results of these should always be the same. And you might ask, well, why this redundancy? Why would we write a function that does this one way or the other? And I don't have a great answer for that. The answer that I do have is that you see the geometric PMF in different forms at different times. And a lot of that has to do with the domain where it's being applied. I learned it as an inclusive PMF, and I never actually messed with it as an exclusive PMF. And then then I saw it as an exclusive PMF, and I was like, oh, okay. But I think it's also sort of an interesting cultural facet. And in practice, you can see it one or the other way, and both ways are valid. Sometimes it's easier to think about it one way over the other way. I don't think we have any problems that look that have that difficulty. Well, that where it would be difficult to think of it one way as opposed to the other way. But at the end of the day, if you use the inclusive form on a problem or the exclusive form on a problem, you should end up with the same result, right? In this case, both of those should be 0.132. All right, so let's just think of a couple more of these. It's good to just think about these in terms of problems. How about this? You're flipping a fair coin. What is the probability that you get your first, heads on the 7th flip? So as soon as you get to an answer, just go ahead and put it in the Slack. Another sort of 1-minute question here. Oh, there's a really good question. Yeah, and I'll answer that question in just a moment. Yeah, so what do you think about this problem? You're flipping a fair coin. And if it's a fair coin, right, then our probability is going to be 0.5. And if we're talking about success as being the first heads, that happening on the 7th flip, well, we could say K is 7. And this is going to lead into the questions that the couple questions that I'm seeing in the Slack, because this is the crux of the thing that we're talking about. And I'm going to say something probably a little philosophical about it, but mostly, and I'm going to try to say something sort of functional about it as well, like pragmatic about it. Okay, so P is 0.5, K is 7. If we, I'm just going to copy this as it is. This will work as it is. If it's inclusive, then we're just using K. If it's exclusive, well, K should be 6, right? Because there's 6 failures before the first success. And when we run this, it looks like we're getting, yep, looks like there's consensus, 0.0078 roughly. Okay, so let me address these questions. Can I explain really quick when it's inclusive, when inclusive is false, I'm passing in k-1. Isn't k-1 written into the equation in the function for else? Now, it seems that way, but that's actually not the case. The k-1 is our conception, right? The k-1 here is a mathematical reality related to including the first success. Does that make sense? So in order to have this balance out, and in asking that question, you're sort of demonstrating exactly why we either say k or k-1, because and what makes these equations equivalent. Why we don't solve that within the equation, we think about it in how we conceive of the problem, right? Like if we're talking about, I've got a good example of why we might think about it in one way or the other. But yeah, this is handled within the problem, and you could make an argument, and I think it's a very fair argument. Well, just settle on how you define k, and that is fair. That is very fair. We could just settle on how we define k, but the reality out in the world is that some people use the inclusive form, some people use the exclusive form, and so when you're talking about this, if you're talking about something that follows a geometric distribution or something that has a geometric process, or even some form of geometric decay, you might be considering, you need to consider how you define this, and that becomes an important thing. We're going to see some slightly more complex reasons why pretty soon, but yeah, we don't want to solve this this version of k. I mean, we are solving it within the equation, but we need to use a different form based on whether inclusive is true or whether inclusive is false. So that said, let's think about a problem that has that's a little different conceptually, right? That might frame this a little bit, this reasoning a little bit better. So how about you have a series of routers transmitting let's say packets of data. So you can imagine, and we're going to be a little bit loose with this idea, but you've got a router, right? And you have an in to the router. Then you have into another router, into another router, and and so on for a while. And let's say that all these routers are the same, and somehow we have equal probability across all these routers that we are going to drop a packet, right? And by drop a packet, I mean, here's this piece of data that's coming through, hits this router. There's a let's say a 99% chance or a 0.9 probability, right, that it's going to be successful through the router. And so here's a case where we actually want to think of success as being this failing, right? The packet being lost, at one of these routers. So if we think about the problem as that, you have a series of routers. There is a 0.99 probability that a given packet of data passes through the router, right? What is the probability that a given packet of data is lost, we usually say dropped, right, is lost in the, let's say the 15th router. So in this case, I'm just making a small argument for this because you could frame this either way. We're thinking about this packet very much in terms of success. Very much in terms of it passing through the router. And we want to think of the packet being lost as being a success because we want to determine this probability that something is going to happen in the 15th router. Now, why would we do that? Maybe if we're performing diagnostic tests, something like that, we're going to think about what this probability should be versus what we're actually observing, right? That's a use case for the geometric distribution in this case. So yeah, let's answer this question really quick. Let's just take a minute for it. And I want you to notice in your own thinking about the problem, are you thinking about it in terms of the passage through the routers, or are you thinking about it in terms of its failure on, or failure being success in this case, right? It dropping on the 15th router. Neither one of those is more correct than the other, but all of us probably have slightly different conceptions of this. And depending on the domain where we're working on these kinds of problems, we're going to take one representation of this problem, or we're going to take the other. Both are completely valid, equally valid. Neither one makes more sense, but some domains will use one, some domains will use the other. Individuals will use one or the other, right? So let's go ahead and solve this. What is the probability, right? The probability here is actually, it's not 0.99, it's 0.01, right? And so we're saying probability is 0.01, and k, maybe if I say k inclusive is going to be 15, right? K exclusive is going to be 14. And we can just call these out as they are. So either we use k inclusive or k exclusive. So I think the world might be like, this would be easier if somebody had just chosen one over the other, right? But they didn't. And so we're left with that, and we want to be left with this understanding that you can use one or the other, but you have to understand how you're thinking about the problem, right, in order to use one versus the other. And it looks like there's consensus on that. So about a 0.8, like a roughly 0.9 probability that we're going to lose a packet on the 15th router. Okay. So it turns out, we've been focusing on the PMF for the other discrete distributions. Geometric, it has a very helpful CDF, and we're more likely to ask a question, say this question. We're more likely to ask this question not in the sense of what is the probability that a given packet of data is lost specifically in the 15th router, unless we, maybe the use case being diagnostic before, right? We want to compare it to the actual thing we're observing. We're more likely to ask the sort of question that is, what is the probability that a given packet of data is will pass successfully through 14 routers? That's a more common kind of question that we're going to think of in terms of this kind of linear equal probability, step-by-step thing that we're seeing here, right? We've got an initial probability, and then it makes it through that, and then we've got the next probability, we've got the next probability, the next probability. And you might be realizing something about this, and I'm not going to say it quite yet, but I'll say it in a second. Okay, so you have a series of routers transmitting packets of data. There's a 0.99 probability that a given packet of data passes through the router, right? What is the probability that a given packet of data will pass successfully through 14 routers? So yeah, how would you solve that? And I'm not asking solve that right now. I'm asking how would you solve this? How do you think about solving it? Yeah, this is sort of tricky, right? It's tricky to conceive of this, and we want to initially think about this as we have a probability of success, right? 0.99, and we can multiply this by another probability, by another 0.99, by another 0.99, by another, right? And ultimately, this is 0.99 to the 14th power. So it's a little bit of a trick question here. Now, what if I were to change this question and ask, what is the probability that a given packet will fail, will be dropped, let's say, before or on the 15th router it passes through, right? So this is clearly an accumulator problem. In this case, in this initial case, we're saying 0.99 to the, say, 14th power. And we're not considering failures, right? We're considering successes, probabilities of successes primarily. So let's answer this second question, and let's answer it through the lens of a CDF. So there are going to be two forms of the CDF that we look at. And in order to understand the CDF, we usually think about it in terms of being an accumulator. So I'm going to have you write a geometric CDF accumulator. How do you relate to the CDF to the PMF? That's the important thing. And this is going to have three parameters, right? P, K, and then again, this inclusive gets true, right? That's the way we're thinking about it. So what is the probability that a given packet will be dropped before or on the 15th router it passes through? How about we just say before? I think it might be easier to conceive if we just say before the 15th router. So you want to think about what we mean by inclusive. Okay, so I'm going to give you 5 minutes on this, and you're going to use an accumulator approach, right? You're just going to call out to the PMF and accumulate from the PMF. So this one is sort of subtly challenging, and I'm going to show what you may have missed in this. So here's our geometric CDF. If we're thinking about what this looks like, let's say we have a probability of 0.5, and we're thinking about inclusive versus exclusive, right? The way that we describe the CDF changes depending on whether or not we're considering inclusive versus exclusive. If we're talking about exclusive, what we're talking about is failures. K is failures before the first success. Well, what if we get a success on the first trial? How many failures are there before the first trial? Well, we have a K is 0, right? So exclusive needs to have the option for K to be 0. Whereas inclusive, if you think about it, if we're talking about up to and including the first success, then we're asking how many failures up to and including the first success. Well, it has a different range of K. And so let's think about this in code. Let's say we're going to accumulate the probability. We're going to say proba gets 0. And really, I should say 0.0. Not that it matters, because we're going to overwrite it. And I'm going to say if it's inclusive, we're going to start counting at 1. And otherwise, we're going to start counting at 0. So notice if we're being exclusive, we can have 0 failures. If we're being inclusive, we can have 1 failure. And that's how we want to think about starting this off. And then I'm just going to do for R in range, and I'm going to do starting at, and then K plus 1. K plus 1 because if we are including K, if we're including the first success, then we want to include the first success, right? K plus 1. If we're only talking about K representing the failures, well, we want to include all the failures up to, that happened before the success. That's still K plus 1. And then we can just accumulate based on the geometric Pmf. So proba is going to get incremented by the geometric Pmf, P, R, right? I'm using R here because we already used K. And I can just pass in inclusive, and that should get us what we need. So we'll return the probability. And let's test this in terms of coin flips. So let's think about it that way first, and then we'll go back and apply it to the prior problem. So let's say you are flipping a fair coin. What is the probability that you get your first heads before or on the 7th flip? Okay. Well, if we want to use the CDF accumulator above, right, our probability is 0.5. Fair coin flip, right? And our value, well, how about this? I'm just going to ask you, if we say inclusive is true, what is our value for K? And if we say inclusive is false, what is our value for K? So for inclusive is true, what is our value for k? Yeah, it's 7. So we're talking before or on the 7th flip. So if we're saying inclusive true, then before or on the 7th flip means we have a success before or on the 7th flip. Whereas if we're saying inclusive is false, then we're talking about failures. We're talking about failures, right? And the maximum number of failures we can have is 6 before the first success. And so we would pass in 6 in this case. So if we're talking about the probability, it might be, I think this is a nice intuitive problem because this probability should be high, you would think, right? Like the probability that we get a heads on the first flip is 0.5. And so we are going to be increasing this probability as we go. And we're really going to be able to take a look at that when we break this out into dictionaries. So let's just look at that. That's pretty high, right? We're going to get we're going to get a heads 99.2% chance, right, that we're going to get a heads on or before the 7th flip. We're either going to get that on the first flip or the 2nd flip or the 3rd flip or the 4th flip. Like it is very likely. So let's go back to this problem above. I'm just going to snag it and bring it down to the bottom. And we're asking, what is the probability that a given packet will be dropped before the 15th router or before the 15th router it passes through? Now, you might want to translate this a little bit. What does before the 15th router mean? It means on or before the 14th router. Right? In other words, on or before the 14th router. And that should make it easier to answer this question. And you might be noticing right now even that sometimes it's easier to think about something as being inclusive versus exclusive. But really, you have to disambiguate these questions sometimes. It's very easy to get your K off by a little bit. So if we're going to use this, well, we can change our values here, right? Our probability of success, right? Success here represents a packet being dropped. That's 0.01. And we're asking the probability that a given packet will be dropped before the 15th router. In other words, on or before the 14th router. So 14 in the case where inclusive is true, 13 in the case where inclusive is false. And it looks like there's a 0.131 probability that we're going to drop on or before, on or before the 14th router. In other words, before the 15th router. Like maybe we're thinking about the 15th router as being some sort of terminal point that, you know, represents the destination. Maybe it's not a router at all. Maybe it's a computer. So this is right. Here's an accumulator approach to solving this. It turns out Geometric actually has a closed CDF we can use directly, and let's just take a look at that. Where is it? See if I have a decent representation of it. Oh, not an amazing representation, but this is good enough. It's not as nice in its mathematical language, but when we're thinking about this, again, we've got inclusive versus exclusive. We've got inclusive up into and including the first success. We have a very simple CDF, right? Well, for both of these, we have a very simple CDF. So I'm just going to code these really quick. I think, you know, these aren't any more complex than what we've already done. I'm just going to call this, I'll hide this. And so I'm going to call this Geometric CDF closed. And we're going to pass in P, K, and inclusive gets true. This time we're not calling out to our PMF at all. We're just going to use this directly. And if it's inclusive, right, this does not look very much different from the functions that, or the PMF function that we wrote. It's a very simple function, right? So is that right? 1 minus P to the K, 1 minus P. Yeah, that's right. Okay. And otherwise, we're going to return a slightly different version of this. Instead of K, it's going to be K plus 1. So let me just verify that all of this is working as we expect it to before I leave you with anything that is incorrect. And I'll just check this with closed. So let's see if that is equivalent. And it is. We can see that that's equivalent. I could put these in, you know, again down here. Why not? I'll just do it anyway. Even though I think it's clear that these are getting us to the same result. And they are. Cool. So something I just want to point out here, you know, one of those, I think I point this stuff out a lot, and I do this for a reason. Notice that these are all the same in the accumulator approach, right? They're different. They end up being different in their precision way out here on the right. And, you know, that's just the nature of computers, right? We, at some point, we don't care. I would even say after this point, all of this is kind of not entirely relevant unless we've got very precise machinery that where we can be more sure of those numbers. But yeah, that comes down to storage on the bit level and the process that led to our computer storing the numbers in a certain way. So we just have slight discrepancies. That does become important in data collection, just to be clear. Okay, so let's take a break. Let's take a 6-minute break, and when we come back, we're going to kind of we're going to look at the geometric distribution in terms of dictionaries, just like what we've been doing previously with binomial and Poisson. I think this is where you really get a feel for what the geometric distribution is. And we'll approach it first with, you know, kind of a coin flipping idea. And you'll see something that looks pretty familiar, I believe. Okay, I'll see you all back here in 6 minutes. Okay, so let's explore the geometric distribution through dictionaries like we've been doing. If we think about geometric like a process, much in the way that we think about binomial as a process, they really aren't that different in some sort of fundamental way. But we can we can think about a geometric distribution as having some sort of exit condition, right? A geometric process is having an exit condition, right? So we've got 0, 0, 0, 0, 0, 1 versus something, right, like 0, 1, 0, 1, 1, 0. If you were to look at both of these, one of those should stand out to you as being geometric because it's all one state before the other state, right? As opposed to binomial where there are two states and there's some probability associated with them. But I'm getting a little ahead of myself. Let's define some dictionaries. So I'm going to go ahead and do this because I mainly want to do this to show what's happening under the hood with geometric. So I'm going to call this, I'll just say Geometric Pmf dictionary. And, well, I'm going to call it the same thing. I could have just written this like this. Okay, so we're going to pass in the probability. We're going to pass in k high, as we've been doing. And we're going to put this inclusive flag in. Although you can see, I think you can see at this point, you know, whether we consider it to be inclusive or exclusive, whether we use one form or the other, it depends on how we're thinking about the problem. It's how we interpret the problem. And at the end of the day, we're going to get the same probability out. So whether or not we use inclusive or exclusive. So let's go ahead and instantiate a dictionary. And I'm going to do this. I'm going to say if inclusive, then we're starting at 1. The same thing that I did before. It's a little boneheaded, but it definitely will work. We could also, you may not realize this offhand, but if you add true to a number, and maybe I'll just show you what I mean here. If I do, so number 5, right? So 5 plus true is 6. 5 plus false is 5. So you can, in Python, you can directly use true and false as incrementers or lack thereof, right? So we could rewrite this to use, and maybe I'll just do that because we have an instance with this logic above, but we could do this just a little bit different. So we're either going to start at 1 or we're going to start at 0. So I could say for k in range, and we could say we're going to do, we're either going to start at true or we're going to start at false, right? So I'm going to start at inclusive, and I'm going to go up to k high plus 1. So this logic is going to accomplish that if inclusive starting at 1, else starting at 0. It's going to do the same thing for us. And then I'm going to say d sub k, right? We're building a dictionary here, so I'm just going to load this with the results from the geometric Pmf, p, k, and whether or not we're being inclusive. We can return the dictionary, and let's consider coin flips, right, or 50-50 chance, and let's look at the progression of the probabilities of k as we increase from you know, low values to high values. And I guess I'll build a dictionary separate from this really quick. We'll set p to 0.5. We'll set k high to, I don't know, let's do 20, let's do 10. Because it's going to become improbable fairly quickly. And I'll just say for k, v in d.items, and we can print the f string k and v. And let's see what that looks like. So this is with inclusive true. Notice what we're seeing here. The probability of success on the first flip is 0.5. The probability of success on the second flip is 0.5 squared. 0.5 to the third power, 0.5 to the fourth power, to the fifth power, to the sixth power. There are times where we refer to this as geometric decay. And in this case, with a probability of 0.5, there's geometric decay. So that's with inclusive true. Let's see about with inclusive false. So maybe I'll rename these a little bit. So D inclusive, make this D exclusive. And I'll just leave both of these uncommented. And we'll traverse D exclusive like that. And let's compare these two. Now, the probabilities don't look any different, but I'm just going to harp on this one last time. How do we describe this? Well, we ask in the exclusive version, how many failures before the first success? Well, 0 failures before your first heads, right? That means the same thing as getting heads on the first coin flip. So it is a semantics issue, and how you interpret the problem and how you represent the problem. Okay. So that gives us a sense of how our probability decays, right? That gives us a very clear sense of that. What about how our cumulative probability grows? I think that's an equally valid lens to take on this in terms of understanding the geometric distribution or geometric process in general, right? So I'll call this Geometric Cdf Dictionary. We're going to go from P to K high, and set inclusive by default to true. I don't think we need to demonstrate inclusive versus exclusive anymore, unless there's any further confusion around it. And we'll say, we'll make a dictionary, and we'll say for K in range, and we're either starting at inclusive or not, and we're going up to K high plus 1. And we can say D sub K gets the geometric CDF, and I'm going to use the closed version. If you have let me just say this really quick. If I'm asking the question, which is better to use, the closed versus the accumulator form of the CDF or of any function, if you have a closed mathematical formulation versus an iterating approach, it's always going to be computationally better to just have your computer do a little bit of math versus traversing some iterable, which is what is happening here. We're traversing this iterable, the range that's created by the range function. So this is a better form of it. But in terms of understanding, just realize that if you don't have the closed form, and this is a theme, if you don't have the closed form of something, well, you can still solve it using an accumulator approach or some other more brute force approach. Okay, sorry, that was a very just a little bit of an opinionated aside. Wanted to throw that in here. So, right, so we're iterating over the range from either 0 or 1 up to k high plus 1, and we're calling out to the closed CDF, the formula version of the CDF, and passing in the inclusive flag. We return the dictionary, and we can call out to that and see what we get. So inclusive, and let's call this CDF. And that looks good. And let's look at this in terms of the inclusive. I think this is nicer to think about in terms of the inclusive because we're thinking about getting a heads on the first flip and not how many failures before the first flip. I think that's more like the way that, well, the way I think about it at least. So if we look at this, we essentially have diminishing returns in the direction of approaching 1. And, you know, something to just keep in mind, it doesn't matter what your probability is here. You're never actually, in a theoretical sense, you're never going to get 1, right? You're never going to get to 1. But a computer, if we have enough trials of this, oops. I'm using, let me just change that. If you're using a computer, notice the computer's like, hey, you're pretty much at 1 by the time you flip the coin 54 times. It will have happened. But don't let that fool you. That's not, this is a precision issue, right? In a geometric distribution, there is no guaranteed, there's no guarantee of outcome, right? You're not guaranteed to get a heads before the 54th trial or before the 55th trial. That's not a guarantee. In fact, you're never guaranteed in a theoretical sense to get a heads if you sit there and continually flip a coin. There is a possibility of getting tails forever, right? So yeah, just be aware of that. It's similar to in a Poisson distribution, it's possible to have, there's a probability, well, a theoretical probability associated with an infinite value of k, even though that is very unlikely to happen. Okay. So that's what we're going to talk about in terms of the PMF and CDF for the geometric distribution. As with, well, especially with the geometric distribution, it's the kind of thing, if we're going to ask you about it, we're going to ask you to solve, we're going to give you the formulas, we're going to ask you to solve textbook problems after having written a PMF or a CDF function, okay? So that's where you might see it in our technical interview, although we'll get more into, yeah, a little bit of more complex math in the pre-course and in the DSI itself in regards to the geometric distribution. Okay. This question, I'm having trouble conceptualizing why for geometric CDF, we don't need to compute a summation to find the cumulative probability. We can just subtract the PMF from 1, but for Bernoulli and binomial, we compute a summation of each probability. Yes. Well, we have a simple CDF. And it's not a very satisfying answer, I know, but when we see a representation, and maybe I'll just see if I can find one really fast, of, say, the binomial CDF, the formula for the binomial CDF. Just going to try to find an image for this really quick. Let's see. Wow, none of these are very satisfying images. Is that? Okay. If I spend too much time trying to find a form of this, it's going to be annoying. So what I'm going to say is, we perform a summation with binomial. That's the way we represent it mathematically. We go for every value of k, and we start that value of k at 0, and then we just perform that and accumulate it, like sum it, and that's how we calculate it. Geometric is just sort of remarkably simple in a way, and because it's so simple, we can we have a closed form of the CDF. For Poisson, again, we use a summation. We don't necessarily have a closed form. Well, it is a closed form when you represent it mathematically, but we still need to iterate over something to get a result for the Poisson CDF as well. Yeah, it's going to be even a little more extreme when we do continuous distributions, because we're going to write something that takes the integral of something continuous and does it within a certain amount of precision. But we even have less to work with. We have less to work with the normal distribution in some sense. And that's our most common theoretical distribution. We think about it in terms of so many different things. We think about it so much that we don't spend much time on it in this class, because we assume you have a sense of the normal distribution coming in. And really, we want you to have an iterating approach to solving it, which we'll get to when we get to. Apologies if that's not a very satisfying answer. But the short version of it is the geometric distribution is very simple, or a geometric process is sort of remarkably simple. So let's get to sampling. I think sampling here, it's going to look a little bit like, it's going to look a little bit like binomial, the binomial sampling. So we're going to use from random, we're going to import random. And I'm going to skip the 50-50, using choice. I'm going to skip that. I'm just going to use random, and we're going to define a Bernoulli trial accordingly. So Bernoulli, if you recall, how do we have a variable probability in Bernoulli? Well, if random is less than p, then we return 1, and otherwise we return 0, right? So does it matter that I'm using less than or equals to here? Do you recall? Which is this more appropriate than using less than or equals? Any thoughts on that? Well, here's the short answer. It doesn't matter. And we're not going to see a significant difference. And, this does relate to continuous distributions a little bit, and we'll talk about that a little bit then. So let's perform geometric in some way. All right. As I said, if we're, well, let me just write some code to kind of demonstrate what I'm getting at here. So I'm going to perform geometric, and let's set the probability to 0.5. And we'll set number of trials. Right, we're just counting the number of trials as we do this. And I'm going to say for whatever in range, and my range is going to be arbitrarily large. I could use a while loop here, but now are we likely to get close to this? No, we're not going to have, maybe if we ran this for thousands and thousands and thousands of years, we would have a nice 2 million for loop run where this fails. But given the probability set at 0.5, we're likely to see, the most likely outcome, or we're going to see the first trial, the number of trials equaling 1 as a very, very common outcome, right? So I'm going to say for whatever in range arbitrarily large number. I'm not choosing that number for any reason. And I'm saying flip gets Bernoulli of the probability. And I'm going to increment the number of trials. And this is a bit longhand, just to be clear. And I'm just doing this to demonstrate so we can see this in action, right? Without me sitting here flipping a coin. And I'm going to say if the flip is 1, then we break, right? Because we're done at that point. Now I could, let's see, I could collect these into a list the way that I might do with binomial, but realize that I would just be, well, I'm going to do that in a second, and I'll show you the fruitlessness of that in a way. So if, let's print success on the whatever trial we find success on. So let's do geometric sampling. Oh, probably need to call the function. Success on the fourth trial, first trial, second trial, fourth trial. I could do this all day, right? I'm not going to, but I could. Okay. So let's, take this a little bit further and say, yeah, I'm just going to define another function that doesn't look much different than that. And again, this is kind of our sampling approach, although, what we're going to end up with, how do I say this? If we're observing something and sampling it in this way, right, we're seeing absent, sort of like failure, success, failure, success. There's a certain point where we can determine if something follows a geometric distribution, right? And that might indicate that we have a persistence of a probability of failure or a probability of success, right? We can do this through sampling and through observation and extract a conclusion such as this is the geometric distribution that we're observing. So I'm going to say number of failures prior to success. That's the form of this I'm going to take. And I am going to collect into a list, even though that is in some way sort of silly. And I'm going to do some arbitrarily large number because we're never going to actually get that far. And I'm going to call out to Bernoulli and pass in the probability. And I'm going to append whatever that flip is. And if the flip is 1, we break. And in this case, I could print, again, I could print the failures up to success. I could think about these lists, but they're all failures up to success. We only care about the count here. So I'm going to return the length of that list. And because I am not including the success, I'm going to say, I'm just considering the number of failures. I'm just going to say the length of the list minus 1. Okay, so let's print geometric with a probability of, like a fairly low probability, 0.005. And let's see what that gets. 362, 402, 1792, 10, right? 367, 449, 2012, So we're sort of observing this process. Let's take that a few steps further. Let's do the thing that we've been doing and pack our samples into a dictionary. And why don't I have you do that? Yeah, I'm gonna have you do that. So let's say geometric samples dictionary. You have these functions above, and maybe I'll copy and paste these into the Slack just in case you're not grabbing this from the GitHub repo. So geometric samples dictionary, and let's do probability of 0.05 by default, and number of samples gets 10,000. And what this should do is sample out to the well, what should we do? You should sample out to geometric above, right? You should sample out to geometric num samples times and pack those counts into a dictionary, right? Your keys should be the value of k. The values should be the counts of that number of k occurring, okay, over however many samples. So let me copy this and I'll put it into the Slack. And I'll give you 5 minutes on it. You might find it helpful to go and reference the binomial sampling materials, but you know, definitely feel free to code this from your current understanding of what's happening here. Are there any questions about what I'm asking here, just to be clear? If you do have a question, put it in the Slack, you know, or raise your hand in the Slack or a thumbs up in the Slack or something within the next 10 seconds or so. Otherwise, I'll go ahead and start the timer. Okay, I'm gonna start the timer. I'll give you 5 minutes to write this. And yeah, do your best on it. Give me a thumbs up if you want, let's say, 2 more minutes on this. Okay, so let's go through a solution here. And let's see. Instantiate a dictionary, right? Pretty much always the first step. And I'm going to say for whatever in range, and I'm going to do this num samples times. I don't need to do num samples plus 1 here, just because num samples, it's going to start at 0. It's going to go up to 9,999. Sorry, brain sort of collapsed inside for a second there. But we don't need that number, and it's going to do this 10,000 times because it includes 0, right? So I'm going to grab the number of failures in general, right? I'm going to call out to the geometric distribution, pass in P, and I'm going to say if the number of failures, this is that same pattern that we've seen multiple times now. If it's not already in the dictionary, we're going to add it to the dictionary. We're going to initialize it, that is, failures. And I can set that to 0. And then increment it by 1. And I can return the dictionary. So we end up with, we're just, the only thing that makes this different in light of binomial is the function that we're calling out to that represents the geometric process. And you can see in general, when we have some sort of sampling dictionary where we're collecting counts, it's basically going to be exactly what you're seeing here if it's observed counts, right? And or observed results. Most functions are going to look almost, if not entirely like this, except for the difference being the underlying process. So let's call out to this. Let's say D gets geometric samples dictionary, and let's use it with the default values here. And yeah, and then we'll just say for K, V in. Notice here I'm going to use sorted, the sorted version of the dictionary. And I can just print, again, K and V. So there are a couple things to notice here that that are, I think, reasonably interesting. Let me just clear that. I'll run it again so that we can see it a little bit larger. Move this up here, I guess. So 471, 485. No, I want you to notice these counts, right? These are going to be consistent. We're going to have values for these. And then we're going to get to a point where we don't actually have samples, right? Where already here, we go 121, 122, 123, 128, 129. And this is just, I'm pointing this out, right? If we were to do more samples, we were to perform more samples, more than 10,000, like if we did 100,000, then we're likely to fill some of these in, right? We're likely to fill in 24, 25, 124, 125, 126, et cetera. But then we're also likely to extend out the end of this and have more things that aren't filled in. And that's, and we do. We can see that right here. We go up to 209 now. From, I don't remember what we were at before. Was it 160 something? Yeah, 160 was the highest one we achieved before. Now we achieve 209. And, you know, I think this is, this may seem obvious, but it's just a further demonstration of if we want to observe something enough to be able to define theoretical probabilities reasonably well, the easiest way to do that is make more observations, keep observing it as much as we can. And, you know, that only gets us so far. And you can imagine that's fairly work intensive. You know, like I'm doing 100,000 iterations of this currently. Well, if I do 1 million, you know, it's going to take some time, right? And it's not that we didn't get there. It's not that we couldn't, you know, get some sort of outcome. It's that it just takes longer, right? In the wild, you don't necessarily have that luxury. Sometimes you can't perform more observations, or sometimes the cost of performing more observations is very high, right? In this case, it's not high because we're just using a computer and, you know, we're just performing some more iterations. It's not so bad. But, you know, I want you to generalize this idea that, of course, more samples is better. And in most cases, you're going to find, especially if you get into, or when you get into neural nets, you need more data. And there's never a point where you really feel comfortable with saying, oh, this is enough. You know, you kind of always want to get more data. And the more, you know, with some of the more classic models that aren't necessarily as performant or don't give you as great of outcomes as some of the more interesting neural nets do, you know, in those cases, you might have 10,000 observations. You might have 10,000 data points. But it still would be better to have 100,000 data points, right? You have a much clearer idea of the phenomenon if you have more data. And yeah, in this case, you know, we're sort of in a rudimentary way showing that, you know, because if you don't know that you can have an outcome of 274, if you only run this 100,000 times, but you do know you can have an outcome of 274 failures as a plausible outcome, you might need to run this 1 million times, right? Or 10 million or more, right? It's just more observations of the phenomenon. So, you know, all that said, let's go ahead and transform this into a sample probability dictionary, just to, you know, show that one more time. If I say, well, we could do something else here too. I'm going to skip the step that we took with binomial, where we sampled from our, sorry, we did multiple trials of the samples dictionary, right? And I'll just indicate that, you know, we could do something like, we could do multiple trials of our sampling approach, right? And then we would fill in a lot of these numbers. We'd have, you know, let's say we did 5,000 runs of this 100,000 samples, and then average the counts that resulted. You know, we would fill in some of these gaps, and we would have somewhat more confidence in what we're observing. But let's just take what we have here and convert this to a probability dictionary. So I'm going to call this Geometric Samples Probability Dictionary. And I'll do 0.05, number of samples at, I'll do 100. Well, no, I'll do 10,000 just to follow the last function. And the first thing I'm going to do is just get out. I'm just going to call out to my samples dictionary. and I'm going to pass in P and the number of samples, and we'll just use that as it is. And then I'll make another dictionary. This will be the thing I actually return. There are more ways to do this than just this. Like I could modify D. It's not so much overhead to just make another dictionary and pack it in. So I'm going to do that. I'll say for K, V in D.items, D sub out or D out sub K is going to get the value or the count divided by the number of samples. And that's all we need to do, right? That's all we need to do to get our sample probabilities out. And then I can just run this. I'll snag all this code. And samples, this will be our samples proba dictionary. And yeah, let's run that and see what we get. And mind you that we're calling this on probability of 0.05. So notice these are very unlikely values up here, and they aren't very precise because it's 1 divided by, right? This is just 1 divided by 100,000 or 2 divided by 100,000. But we can, if we observe this phenomenon enough, if we do multiple trials of these samples, then we might be able to describe the phenomenon in terms of the probability of a certain number of failures before the first success. Yeah. And all we had to do here is divide the count by the total number, right? That's how we're getting the probability in this case. Okay, so we've got about 12 minutes. Let's see about maybe writing some problems. I think, yeah, why don't we do this? I'm going to go into geometric problems, and I'm going to import from geometric using Pmf. I'm going to import everything. Okay. So if so that way I can just use those when I encounter them. And let me make sure I'm not printing anything. Doesn't look like it. And we'll find out anyway if I am. Okay, so I've got a couple of the breakouts copied over here. And let's just, okay, so suppose you have an unfair coin with a 68% chance of getting tails. What is the probability that the first head will be on the third trial? As soon as you get to an answer, go ahead and put that in the Slack. And the first thing you might ask yourself is, what is the probability of success? Anybody have a thought about that, or want to throw out the answer? What is the probability of a single success in a Bernoulli trial in this case? Yeah, it's 0.32, right? It's because we're describing the chance of failure. The only reason this is failure is because heads represent success, right? So P is 0.32, and then I can use the inclusive form. I can say K is 3, and let's find out what this is. So geometric Cdf, no, geometric Pmf. P, K, and we'll just set inclusive to true. I'll just be explicit here about that. And let's print the results. Uh, 0.147, so 0.148. Anybody else seeing that as a result? Okay, so that's, there's some consensus on that. And there's a number of these problems that I have. So why don't I'm gonna fill all of this in a little further after class. I'm just gonna paste a bunch of stuff in here. One thing I'm gonna paste in here is a solution to one of the slides in the geometric breakouts that I think is kind of interesting, mostly because you have to kind of consider some things about the problem. It's just some extra practice if you wanna do that breakout. I don't remember which slide. Well, I can just tell you what slide it's on. And then I'll put the solution in here for that. I think it's somewhere here. Nope. Ah, yeah, it's this. It's characterizing severity and risk of drought. There's a cool question in here. Given that there is a drought, what is this probability? That's kind of tricky. So this is what? This is slide 17. So I'll indicate that. Geometric breakout 2. I'll put that in these notes if you want to take a look at them. But the kind of the big thing that you're going to want to be able to see is the difference between binomial Poisson, geometric, and say basic probability. And I'm going to give a number of, just a small handful of problems in here, kind of demonstrating that. So let's think of a binomial problem. Binomial. In general, what we're asking here is, what is the probability that some number out of some number of events is successful? Right? You have 20 events. What is the and the probability of success on any given event is 0.3. What is the probability that 18 of those 20 events are successful? That's what that looks like, right? And what you need in this is, you need a probability, right? So that probability could be, I don't know, what did I say? 0.3 is the probability of success on a given trial, right? You need the number of trials, and I think I said 20 in that case. You might ask, what is the probability that 18 are successes? And the story is not here, right? The story of this problem is not here, but when you get down to it, that's all you need. And this is going to be the binomial Pmf for P n trials and 18 successes. I think we usually do, I think we wrote it as NPK actually. So P n trials, which we'll just call N actually, and 18, which is our K. So that's the nature of binomial. Geometric, we can describe as being, the probability of some Bernoulli trial or binary event is P. What is the probability of having your first success on the nth, let's say the kth trial? Well, I like thinking about this as the nth trial because you exit at that point, right? So it's either going to be true or false. It's either going to be success or failure. You have a probability of success known somewhere, and you're asking, what is the probability of having your first success, or some count of failures, before some nth trial. So I think I'll leave that as K. And when we think about Poisson, we're thinking about some question in terms of a known volume of time or space or something, right? We have an average, and often this is going to look like, on average, some number of events happens in this volume of time, space, whatever it might be. And we're asking, what is the probability that, of some other, potentially, other value than the average, some other number of events happening in this volume, or in some expansion or contraction of this volume. And, this is just sort of template, right? These are templates for certain kinds of problems. Now, you also have basic probability problems, and it's easy to get confused sometimes between basic probability problems and these distributions problems. And sometimes basic probability is a way to solve one of these problems, right? So out of 20 trials, what is the probability of getting all failures, right? If you have a known probability of success for a given trial. Well, you can just exponentiate the probability of failure to 20, and that's going to answer your question. And so you don't need to jump through, you don't need to apply the binomial PMF in that instance. But if you did, it would get you the same answer. Okay, so I'm going to fill this in just a little bit, just some notes, and template problems for these. And I just want to say that we don't stress geometric as heavily as we do binomial and Poisson. The reason being, you can kind of derive geometric, and we kind of use geometric as a means to explore certain kinds of coding problems, right? And the semantics of geometric, which is probably just frustrating, but it's also the kind of thing that comes up a lot in our space, in the data science world. There are a lot of different ways that we represent and discuss the same problems, depending on domain. Cool. That's class for today. Tomorrow is going to be a pen and paper class, primarily, in the sense of we're going to cover conditional probability, and we're probably not going to do any coding, or if we do, it's going to be very minimal. So that's going to be exploring conditional probability, Kolmogorov, and Bayes' theorem. Stay on if you have any questions. I can't stay on for very long. I have about 5 minutes, but I'll be able to stay on longer tomorrow. So yeah, stay on if you have any questions. And otherwise, have a great night. All right, I don't see any questions coming in, so I'm gonna go ahead and sign off. Have a great night, everybody, and I will see you tomorrow.